Can you guys hear me okay when I talk for a bit?
Yep.
Yeah.
Sweet. I'm going to switch over to the. I'm going to switch over to the. Oh, can we, Tom, can I switch over to the?
You find that other
Thank you.
source? Come on, find them. There you are.
Okay, and I'm gonna share just to. Ah, sweet. And we're good to go. Okay. Thank you, Ronnie and the SBAU for having me out here. I also want to say thank you to my advisor, Andy Howell at LCO. He's given me a ton of freedom to work on this stuff as my side hustle. And I just want to say thank you to my advisor on this project, Alex Lipsaska. But I also have a special thank you to you guys. So to give me a chance to talk about this stuff tonight, I'm really genuinely excited about this work, and it's such a privilege to be able to talk to you all about the Black Hole Explorer and where the space mission stands and what we expect to see. And you know, it's been a dream of mine since I was a child to work on a space mission, and so it's kind of hard for me to believe that I get to stand up here and talk about this really cool project. So thank you guys so much for being here. Let's get into it. Okay, so if you've already read anything about cosmology, about our picture of the universe, you probably picture something like this: a universe that's expanding like a balloon. It's got no boundary. And that no boundary comes from the fact that, if you lived on the surface of a balloon like this, you wouldn't really perceive any boundary because you just keep walking around and around and you wouldn't fall off an edge, unlike the Earth. But actually this picture overlooks something, which is that the universe actually does have an edge, not in the flat Earth way. So what do I mean by an edge? Well, we have this property of the universe that massive objects attract each other. This is called gravity. And Einstein showed us that with general relativity, that a massive object bends space-time around it, and then other objects kind of fall into this gravitational well, this dip, and appear to interact. And the effect happens on small scales, like as small as tiny particles interacting. I made my students do a calculating how weak the gravitational force is relative to the electromagnetic force, and it works on that scale too. But also, and I'd argue more importantly, sorry, Liam, on large scales, on the scales of the universe, the largest scales of the universe, and gravity actually is the largest. It's the most powerful force in the universe because on large scales it can't be stopped by a negative mass. So even though the forces like the electromagnetic force or the strong nuclear force are many, many, many times more powerful than gravity, because you can have a positive charge cancel out a negative charge, they can go to zero, but nothing really ever takes away the force of gravity. It just keeps going on and on and on. Gravity has this unique property, or not unique, but it's got this nice property that it only ever attracts. So the more mass you get, the stronger the gravity becomes, and that attracts more mass, which makes the gravity stronger. And there isn't really a limit to how strong the gravity can get. There are practical limits, like how much matter there is in the universe or around you, but there isn't a theoretical limit that says, oh, here's a cap. Eventually, if you keep shoving more and more mass together, the gravity's going to get stronger and stronger, and eventually you'll get an object that you've probably heard of, a black hole. And a black hole is this object that has so much mass that it's compacted in such a small space that not even light can escape the pull of its gravity. And that sounds like a really mind-blowing concept, but to be honest, that's not even that weird. Ever since we understood gravity, which has been for a pretty long time now, a couple hundred years, we've understood that the more mass you have, the more gravity you'll have. The more gravity you have, the higher something called your escape velocity will be. So, if you want to escape the gravitational pull of a massive object, you have to travel faster than its escape velocity. For the Earth, that's about 7 miles per second. So if you want to send a spaceship into space, you got to achieve a 7 mile per second velocity. So it's not that crazy to think, okay, you keep putting mass in, you'll eventually get past the speed of light, which is very finite. And actually, in the 1700s, the idea of a black hole was hypothesized. It was called a dark star, a star that tried to emit light, but its gravity was so strong that the light would just fall back on its surface. So black holes are interesting, but they're not even that weird until you get to sort of the advent of general relativity and our subsequent understanding that gravity is an effect caused by the curvature of space-time itself. And it was then we realized that something strange happens inside a black hole. So as the mass grows and grows, its gravity gets stronger and stronger, and the curvature of the universe becomes more and more extreme. Eventually, you get an event horizon where, because you can't travel faster than the speed of light, no signal can escape beyond this region. But right at the center of the black hole, the equations that govern the curvature diverge to infinity, producing this weird thing called a singularity. And in a strange moment, the universe kind of bends and bends and bends and bends, and then it kind of just rips at one point. And that's at the singularity at the heart of the black hole. You can almost imagine a little pop as this point that was once in the universe gets removed. What do we know about the singularity? Well, we know it's an inevitability. It's not so much a point in space as it is a point in the future shared by all travelers who enter the black hole. Anyone who falls in, the singularity inevitably lies in their future. But it's really weird. It's this spot in the universe that you can reach in finite time, but it doesn't exist in the way other places in the universe do. It's in GR, we'd say it's a point that has been removed from the manifold of space-time. I find that so weird. It's so weird. In a very real sense, it represents an edge to the universe. Not an edge you could go to and wave to someone on the other side, but a boundary where our understanding breaks and space, time, and predictability kind of cease to be meaningful concepts. Ever since I've learned that our universe has an edge, I've been really desperate to answer 3 questions. What does it look like? And can we take a picture? And Instagram. And what lies beyond? So we can try to answer these questions with 2 theories that we have that describe the whole universe. Einstein's general relativity, which we use for really, really big objects, and quantum mechanics, which we use for really small ones. The difference is much more nuanced than that. But that kind of covers it. Like, if you were talking about the orbit of planets in the solar system, you use GR, you wouldn't ask QFT. And if you were talking about an electron passing through 2 slits, you'd use quantum mechanics. GR would be functionally useless. And they work really well, these 2 theories, and they, together, describing all the big, the small, the slow, and the fast, they kind of cover our whole universe. And they work really well. And that's not a good thing. And I'll explain why. So we've tested them again and again and again across so many scales and regimes. I've just selected a couple of the many, many experiments that we've done to prove that these theories work extremely well, to highlight just how correct these theories are. So, the classical GR test is the Eddington experiment. Einstein predicted that light should curve around massive objects in a very specific way, because even though light has no mass, and so maybe it shouldn't be affected by gravity, if you imagine that gravity is the curvature of the universe, well, light's going to follow that curvature regardless if it has any mass or not. So, Einstein predicted that if you look at some stars in the sky, and then you look at them again in a solar eclipse, where the sun is there, but it's not blinding you with its light, the stars will have moved. Their positions will look a little different because their light is being bent, like the light bends through a pool of water, by the sun's gravity. And he was exactly right. Eddington went out and did this experiment. He schlepped out to take some data during a solar eclipse, and he found that Einstein was exactly right. It's like 1%. And then we got even better experiments like Gravity Probe B, where we had these incredibly sensitive gyroscopes around Earth, and we pointed a telescope inside the satellite at a star, and we had predictions for how much Earth's gravity, based on general relativity, would wiggle the telescope as it looked at the star, and it exactly matched predictions. So Einstein was right again in one of the most sensitive tests of general relativity ever. But quantum field theory, quantum mechanics is no slouch either. In the early 1900s, people were coming up with experiment after experiment to show these incredibly bizarre properties of light and particles, that everything in our universe kind of behaves as both a wave and a particle. That evolved. We have so many experiments testing this, but very, very recently we had the muon G-2 experiment. And they showed with incredible precision that the muon, which is a heavier electron, wobbles in a magnetic field to test the predictions of the standard model, which we have someone in the audience, Liam Brennan at UCSB, who works on this kind of stuff. And even the tiniest discrepancy from the standard model could be detected many, many orders of magnitude of precision, higher than any experiment before. And had there been a deviation, it would have pointed to new physics. But boringly, the standard model was right again. And so even on the most, the finest scales, the highest precision you can imagine, these two theories are right over and over and over again. For all intents and purposes, that is correct. That's their truth, is how we can think of it. And that's really important because we've used these theories a lot. And very bad things happen if they fail. So like your cell phone is entirely like based on the principles of quantum mechanics, how we're able to squeeze tiny high resolution screens and processors into a device the size of a potato chip. That's all quantum mechanics basically. And then how that device connects to satellites orbiting Earth at a non-trivial fraction of the speed of light, causing them to experience time dilation and slow down, all general and special relativity. And more so than just useful things, which personally I have no interest in. These theories also give us all the information we have about how the universe was born, like all the way up to 10 to the minus 135 seconds after the Big Bang, which is a very, very short amount of time. All the way to how it evolved to its present day, going through its stages of radiation, matter domination, now dark energy domination as it accelerates continuously, until its eventual death, as everything eventually gets sucked into black holes, and then those black holes evaporate via Hawking radiation, leaving behind a sea of colorless noise. Sorry. That's it a long way away, so continue to enjoy your lives. But all the stuff that I just said, which we're pretty sure about, is based on these two theories being right. So I hope I've convinced you that it'd be really bad if either of these were wrong. Okay, so why do we care about whether or not they're, why am I bringing this up? Well, black holes are kind of weird, right? I said that we use GR for really big stuff, and we use quantum mechanics for really small stuff. That was an oversimplification, but not by that much. To give you some perspective on how big black holes are, and you'll see why I'm bringing this up in a second, if the average human being is about 10 to the 1 kilograms. If you're in America, probably more like 10 to the 2. For comparison, the Earth is about 22 orders of magnitude heavier than that. So take 10 followed by 24 zeros, or 23 zeros, and that's how big the Earth is in terms of mass. And if you took it and squished it into a black hole, you would get a black hole about the size of a marble. So that should give you the idea of the density that you need to achieve a black hole. You can do the same thing with the sun, and we found lots of stellar mass black holes thanks to LIGO and stuff. And if you did the same thing, you compressed it into a black hole, which we now know we can by a supernovae, you would get a black hole about 2 miles across, which is about the size of Manhattan. So black holes are these things that are both really, really, really heavy and squished into a tiny, 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 tiny space. So you can kind of fairly say, you can ask both of these theories what happens. And a black hole is actually the only place in the universe where you can fairly ask what happens. You fairly ask both of these theories for an answer to the question, what's going on here? So we do that. We ask general relativity, hey, once you get past this event horizon, what's going all the way down to that singularity, that edge, what's going on? And you can ask quantum mechanics the same thing. And they disagree. They give completely different answers, and honestly, to some extent, the answers are kind of nonsense. And that is really problematic, because now that we know black holes exist, we know that there's a place in the universe where we're wrong about these two extremely important theories. And so a great mystery emerges. Which theory is right? Are they both wrong? Which would be a catastrophe, and it was also the most likely correct answer. Honestly, we're lost. Like, this is the greatest open mystery in physics, the disagreement of general relativity and quantum mechanics in the most extreme environments in the universe. We've had attempts at trying to resolve this. You may have heard of some of them. One of them is called string theory. It's a kind of a nice pop-sci topic, but it's an attempt to come up with a theory of everything that doesn't start from assumptions that violate the other theory. So, quantum mechanics kind of starts by assuming that the universe doesn't really curve, and that's like already a problem. And general relativity is like, kind of assumes that everything looks the same on all scales, and the universe is just one smooth mesh. And both of these assumptions violate the other theory. The theories like superstring theory and loop quantum gravity try to say, okay, what if we started with all the assumptions from both theories and built a common theory that And they've made real good progress, but we're nowhere near a testable theory. Part of the problem is, how do you test this, right? GR and quantum mechanics work super well on every scale we could possibly probe, and where they fail is a scale that we don't really have access to, black holes. So we can't really test out of these guys, but there's another route. We can't create a black hole on Earth, but some of us went in a different direction. Can we try to take a picture of one and use that to test these theories in an experiment many times more intense than anything we could hope to create in a lab? So that was what the goal of making these kinds of images is. Can we try and take a picture of this edge of the universe? What do we expect it to look like? Can we get a clue about the mystery of whether GR or quantum mechanics is right? And that's what began the race to see a black hole for the first time. So, astronomers for decades have been looking around the universe for what they thought were good spots to find black holes. And one of the easiest targets is the center of the Milky Way galaxy. In every galaxy we've ever looked at, there's a big, big, big black hole in the center of it. There stood to reason that there'd be one in the center of ours. So we found the brightest spot in the center of our galaxy that had a bunch of stars orbiting it. And we zoomed all the way in, and spoiler alert, that's our picture of the black hole in the center of the Milky Way. I've sort of told you already that, black holes are really, really small, and they're also really far away. So out of curiosity, who here has seen the first image of a black hole, the one that doesn't look like this, M87? It's like also a fuzzy orange donut, but okay, yeah. So that one was way farther away than this one. This one is just 25,000 light years away, but M87 was 55 million light years away. And I just told you that black holes are really small. So a fair question is, how do we create these images? And so I'd like to introduce you to something called interferometry, which is basically magic, and no matter how long I work on it, it will never seem to be less so. I'm working on it for a better part of a decade now. You guys are I know a lot of you guys are really familiar with optical telescopes, but you may be less familiar with interferometers. So let's do a quick review. This is a telescope. It has a certain size, d, and it observes at a wavelength, lambda, which is, for optical wavelength, that might be 550 nanometers. For radio wavelengths, it might be like 1.3 millimeters. But the point is its resolution, which is how small of a thing it can see on the sky, scales with these two numbers. If you want to get a better resolution and see something sharper, you can make your telescope bigger, or you can decrease the wavelength that you're observing at. For the purpose of this, let's just think about making the telescope bigger. Interferometry lets you connect two telescopes together into a network, or an interferometer, and their resolution is now no longer a function of how big each telescope is, but rather the distance between them. And this immediately leads to a life hack, which I'll explain in a second. But there's a little problem. Even though it's really convenient, right? You don't need to build a huge telescope. You can just take two small telescopes, link them together via this witchcraft, and place them on opposite sides of the planet, and you've got an Earth-sized telescope. But there's a slight problem, which is that when you do this, the telescopes no longer can see the image of the black hole, of your target, like a regular photo your camera would take. They instead see properties of the wave that bounces along the line between them. This line between them is called the baseline between the two telescopes. And the quantity that the telescope sees is now no longer this, brightness on the sky, it's this complex quantity telling you how powerful the electromagnetic wave is and its phase. It turns out that quantity is intimately related to something called the Fourier transform. So if you take an image of your source and then Fourier transform it, which is this mathematical transformation that tells you how to make this image out of a bunch of sine waves, that's what an interferometer sees. So you can imagine your baseline has some size and angle, and it turns out that the size of the baseline and the angle it observes at, this quantity v that it measures, is exactly the brightness of that point in the Fourier space. This is not that important to really internalize. I'm just trying to communicate how weird, how much harder it is to make an image out of this, right? Because we now have to invert this thing to get our image out. And that's fine if you have all the information, but we don't. What I just showed you here is we spend tens of millions of dollars and put two telescopes to get one data point. And you need all the data points to try and invert the image. We have tricks, so if you place many telescopes together in a network, they each have baselines connecting them, and then those baselines probe different parts of the Fourier transform. So if you start placing telescopes all over the world, which is what we did, you get this dense network of baselines, and you can probe that weird Fourier transform thing and get an image out. And it's a blurry image, because you don't have all the data, but you need to make a really sharp one, but it is an image nonetheless, and a real image. You may have heard that it's like a fake photograph, or it's not real, or it's a simulation. It's not. It's a real image, but like a telescope doesn't have glasses on. So you can see the life hack here is we took telescopes and put them as far north as we possibly could. That's our telescope in Greenland, and as far south as we possibly could. That's literally our telescope at the South Pole. And as far east and as far west as we could. We have two telescopes on Mauna Kea in Hawaii, the sub-millimeter array and the James Clerk Maxwell telescope, and telescopes in Europe, at IRM and Noema in Spain, and I forget where Noema is. So the fair question is now, what kind of resolution? We've done all these tricks. We've accepted the burden of having to invert this magic Fourier transform thing and get our image back out. The question is, what resolution did this buy us? How good can we see? So let's first give you some perspective. The human eye, the little thing in your head, has pretty good resolution for an organic, ball. And the way you can think about the resolution of the human eye is if you took a credit card and stood on the opposite end of a football field, you'd be able to see that the person is indeed holding a credit card. You wouldn't be able to see the numbers or anything, but you could see like a vague, capital One colored rectangle. And so that's about the human resolution of the human eye. A credit card at 300 feet. I'm at 20 minutes, so I want to do a quick check-in. You the guys. Last time I spoke here, I gave Eminem's Rap God a run for his money because I talk too fast. Is this one going better? You guys know? Okay, sweet. All right. Okay, so that's the resolution of the human eye. What about a home telescope? The SBAU folks in here probably recognize this. You can get it from Best Buy, and it's like a nice starter telescope, a Bird Jones design. So the image is crap, but this was one of my first telescopes ever, and I still love this thing. It had a little mount you could put your phone on, and it would show you. It was a great, wonderful gift. And anyway, if you this is like a $200 telescope you can get, literally just walk into Best Buy and get, and it could see a credit card. If you were standing at my house in Goleta from where you're sitting right now. And that's pretty impressive. So you go 10 miles away and hold up a credit card, and you can see it pretty decently with this telescope. Again, no numbers or anything, but you can see that you're holding a card. Now, what about something proper like the Hubble Space Telescope? Well, now you can see a credit card. If you can see like the Hubble Space Telescope, you can see a credit card in LA from where you're sitting right now. So the question is, what are we talking with the Event Horizon Telescope, right? How much more resolution do we buy? How far away do we place this credit card and still see it with the EHT? Fun fact, guys, I grew up most of my life in Boston, Massachusetts. And if you hopped on a plane and flew all the way out to Boston and then landed and held up a credit card, the EHT would be able to see it from where you're sitting right now. But unlike all those other telescopes, EHT would be able to read the numbers off the card for you, and steal your identity, which is the real reason we built it. But that's it. That's the resolution that we gain going to this interferometry approach. You go from being able to see something 100 miles away to being able to see it across the country, and that's how we go from being able to see large galaxies that are far away with great detail to being able to see a tiny black hole in a dusty elliptical galaxy 55 million light years from Earth. Some more analogies. If you could see like the Event Horizon Telescope, you'd be able to see Neil Armstrong's footprint on the moon from where you're sitting right now. Another equivalent is you could see an atom held at arm's width. Wow, that atom did not show up well. But kind of think about that, right? If you hold out your hand and there's an atom there, you'd be able to see it. If you could see like the Event Horizon Telescope. That's the resolution we're gaining. And it's that life hack of interferometry that gave us these two images that you've seen, the first and second images of a black hole. They're fuzzy orange donuts, and even with all that resolution, they're just enough to see this black patch in the middle of both called the shadow of the black hole, where light goes in and it never comes out. But it's enough to confirm that there is indeed a black hole there and not some other weird horizonless thing. And to the best we can tell with this, GR seems to work. It matches predictions. But we have to admit that this image is a little blurry. We did a lot of outreach after we released the images, and one of the common, very endearing and well-meaning comments we got was people telling us like, "Did you try playing with the focus?" And we did. The images that you're seeing here are actually just 4 by 4 pixels across. So they're just 16 pixels, just enough to see that shadow. And that's why they look so blurry. But don't worry, this 16 pixels cost about $80 million US, which sounds crazy, but then you remember that this image was seen by about 4 billion people, thanks to Google putting it as a Google Doodle, and it's used as people's profile pictures and for memes. Not that memes are worth $80 million, but like in terms of reward to cost ratio for impact on the world, this is like the highest in science, period. Like the LHC $1 billion project, Hubble Space Telescope $1 billion project. So this is actually pretty cost effective. Okay, so it is blurry. So all of us were thinking, even though it matches predictions, like this is a general relativistic magneto-hydrodynamic simulation, which basically means it takes the principles of hydrodynamics, which is like fluid flow, and then adds in magnetism, and then adds in general relativity, and you get very accurate simulations of what we expect the world around a black hole to look like, and they look exactly like what we got. So GR seems to work, but it is blurry. So what if the image wasn't that blurry? Could we go sharper somehow? What would we expect to see? So we took our GRMHD simulations, and for example, these are provided by Charles Gammy at the University of Illinois Urbana-Champaign, and his wonderful students. And we can make these simulations of all kinds of black holes. And not a lot we can get from that. Like, they kind of just all look different, which is not good. We're looking for features that we can latch onto and say, this is something we want to see. But something really cool happens when you take all these simulations and then you average them in time, and you look at the average image. All the moving stuff goes away, and you're just left with this incredibly thin and bizarrely bright ring of light, which is not something you'd expect for an object that supposedly sucks in light and never lets it back out. Instead, you get this perfect circle of light, and this circle of light is visible, looking exactly the same, no matter where you view the black hole from. So that's kind of wonky, right? There's nothing else in the universe where you look at it from every angle and it looks exactly the same. But this little ring of light does do that. And it turns out this ring of light, we gave it a name, and we called it the photon ring. And it's created by a very special and amazing process. So a black hole's gravity is so strong that it bends the light that's traveling around it. So here's a little animation of what that looks like. If you imagine light traveling from around a black hole, some of it's going to get very weakly lensed. So we call this direct emission. And basically, it makes up the majority of the light that goes around the black hole. And it's not that sensitive to the black hole's gravity because it's only getting weakly bent. But if you get just the right trajectories, some photons will orbit half-time. We call these an n=1 photon because they orbit 1/2 times around the black hole. And because they're on a narrower set of trajectories to achieve this half orbit, they create a thinner, brighter ring. And you can keep doing this. What about photons that execute 2 half orbits or 1 full orbit? Because this is the n=2 photon ring, and it's even thinner and brighter. And when you add all of these photons that are orbiting together, you get the image that we saw, where you have a sort of big field of emission, and then on top of it, no matter what angle you're looking at the black hole from, a crystal clear ring of light, the photon ring. So these photons are coming from, this ring of light is coming from photons that are being forced to orbit the black hole due to its gravity. So everyone was really excited about this. In 2020, there was a huge burst of excitement for trying to understand this photon ring better. I, along with my collaborators, published a theory paper showing that you can make precise measurements of a black hole's spin from the shape of its photon ring. So it looks very circular, but actually it has a slight deformation, and we can use that to measure spin. And then at the same time, a team at the University of Arizona, led by Sam Gralla and Alex Upsaska, both of whom I now work with, they showed that you could actually measure shapes like the photon ring using interferometers in a very beautiful and elegant way. And then they published another paper showing that you could actually measure this shape precisely enough to test general relativity and measure things like the black hole spin. Then my current supervisor, my supervisor at the time, Michael Johnson, Alex, and a bunch of others who were working on photon ring science, published a paper that would kind of set everything off. It was called Universal Interferometric Signatures of a Black Hole's Photon Ring. And we proved that you could measure the photon ring of a black hole in the center of the Milky Way if you took the Event Horizon Telescope and extended it to space. So that's how the Black Hole Explorer was born. We realized that with sufficient resolution, you could measure this shape. When we did this calculation, we did run into a problem, which is that the ring is very thin. So we do these simulations, and with the Event Horizon Telescope, we could get this image out. But how far into space would we need to go? How bigger than the Earth would we need to go to get this image out? And obviously this is a problem because the Event Horizon Telescope was already the size of the Earth. So anything else is going to be a challenge. But this was the birth of the BEX project. The Black Hole Explorer, in the next 10 years, will launch. We're going to design and develop and launch this orbiting radio telescope. It will have an orbital radius 3 times larger than the Earth itself, which will give us enough resolution to see those amazing photon rings. And it will interface with the Event Horizon Telescope and take the first image of a black hole's photon ring, getting us closer than ever to solving this mystery in physics. So it will help us bring our images from this to something more like this, where you can very clearly see the photon ring. So once we have this telescope in space, we'll be able to make images like these. And we're building this thing right now, like at this moment. We just got finished up a conference in Japan a couple months ago. These are some of the leaders of the collaboration. I'm up there in the Zoom meeting. I was unable to make it to Japan, but it's a huge team of people. It's a global telescope, now a space telescope, so it takes a global collaboration. So we have over 150 members, dozens of countries and institutions, all collectively working together to build this space telescope. And we've got prototypes of the dish, the communication system, all this stuff going. And we're right now in the process of submitting a $270 million NASA Small Explorer mission proposal, which will allow us to build the telescope and put it in space and make this really cool image. And this has been an amazing experience because I've always wanted to work on a NASA mission, but it's definitely very intense. NASA is they're very engineering minded. Scientists are very idealistic and like to kind of just get all loopy about stuff. But engineers are like, what can you do if this breaks? Or that. And so NASA has these things called technological readiness levels, which we have to meet progressively as we go through this proposal process and building the spacecraft in order to convince them that we're ready to fly. And I want to share this because there's a really funny analogy for the TRL stages. If you're imagining, finding a unicorn, TRL 1 is like, just kind of asking, what if unicorns were real? TRL 2 is, we haven't seen a unicorn, but we've drawn one. That's like our simulations. We know what we expect them to look like. TRL 3, we have made a unicorn in CAD. And we think this is a final design. TRL 4 is all about the prototype, so we've taken a horse and then placed a horn on it. And it looks kind of like what we said. TRL 5, we put the horse outside, and it seems like it's still surviving. TRL 6 is like, okay, you've made it, you may now call it a unicorn. And then TRL 7 through 9 is, can we launch it into space at a high velocity? And then TRL 9 is like, full success. So it's very different from kind of what I'm used to in the science world, where you should do a proof of concept with some simulations and you're done. But it's really amazing and intense experience. So what will we be able to do with VEX? So the goals of VEX, we have 3 primary goals. One, we want to answer the question, how do black holes look? We know how they look with massive myopia, but we'd like to know how they look if we play with the focus a bit, get the subject from the background nicely separated. And that's kind of my area of research, is the photon-ray stuff, using it to measure spin. I'll get more into that. But the next question we can answer with VEX is, how do black holes shine? So one thing I haven't talked about at all, because it's not my primary research interest, is black holes launch these massive jets. So one of the really fun things about M87 and why we thought there was a supermassive black hole in that galaxy was, if you look at images of it, you can see a huge jet coming out of it. And this was spotted back in the early 1900s. And it turns out we've taken images all the way down, and the black hole is causing that jet. And we don't really exactly know how we go from a black hole, which is supposed to suck everything up, to basically a giant pump hundreds of thousands of light years across. And we would like to know how that works more, because that's important for questions about the evolution of the universe. As is our 3rd mission goal, which is to answer the question, how do black holes grow? So with the Event Horizon Telescope, we, with all that resolution, all that money, all that work, is 350 people from around the world working for over 2 decades to build the Event Horizon Telescope. We got 2 images, because those are the 2 largest black holes on the sky. Even at our resolution, we can't see anything else. Everything else just looks like a fuzzy blob. But with VEX, we can make dozens of those donut images. We have a figure in our proposal that we call the donut tray that shows all these simulated donuts we can make for many black hole sources. And if you can see the donut, you can make inferences about the size of the black hole, its spin, and all this stuff. And that's really powerful, because if you can measure a black hole's spin and its mass, you can learn stuff not just about how black holes grow, but how the universe grows. So for example, if we look across the universe and we find that supermassive black holes have very high spin, it tells us that they get their spin by sucking in stuff, and the angular momentum of that matter that they're sucking in contributes to the black hole's angular momentum, and they keep spinning faster and faster and faster until until they hit their limit, basically. But if you've ever played pool, you know that when you put top spin on a ball and it hits the edge of the table, some of the spin gets taken away, and it's spinning a little slower when it bounces off. And it turns out the same thing happens with black holes. So when black holes collide, unless they are exactly oriented the right way, which is very unlikely, they lose angular momentum. So if we survey the universe and we find, all the black holes we see have low spin, they're spinning very slowly, then we know, okay, black holes are forming and growing to the size by merging with other big black holes. And we've seen pictures of this where galaxies are merging and there's supermassive black holes coming to merge together. So there's so much science that we can do with VEX. Here's some stuff about the mission itself. This is a preliminary render of the spacecraft by Lockheed Martin, which will be helping us build the spacecraft along with a lot of other amazing institutions. But the idea is we're probably going to have an antenna that's about 3 meters in size, which doesn't sound that big, but we have pretty good noise budgets because we're in outer space and we don't have to worry about the atmosphere or people leaving their porch lights on. So we're good. And we're going to observe simultaneously at 2 frequencies to maximize our data output. And we will have an orbital altitude of 20,000 kilometers. So our longest baseline will be about 20,000 kilometers plus the diameter of the Earth, so about 26,000 kilometers. And that is much, much larger than the EHG. That's the radius of the Earth is 12,000 kilometers is the diameter of the Earth. Where's it miles? I'm sorry, guys. I'm forgetting how big the Earth is. I've been staring at so many numbers for this proposal. But at the end of the day, we're going to achieve around a 6 micro-arcsecond resolution via this hybrid space-ground interferometer. To give you some perspective, the EHT resolution, which got us those wonderful black hole images, was about 20 microarcseconds. So we're going from 20 to 6 just by putting the spacecraft into orbit. And we're planning to launch in 2031, and when we do, our orbital configuration will look something like this. So we're going to have all these red points correspond to components of the Event Horizon Telescope that we'll be interfacing with, and these yellow stars correspond to our data downlink, which I'll talk about in a second. But VEX will follow these orbits and connect with different parts of the telescope at a time, over time helping us flesh out that Fourier transform and get more data to convert into a sharper image. And we hope to be able to go from images like this to images like this. And if you compare it to a raw simulation, you can make out, just barely, the photon ring itself from the background. And that is extremely exciting, because that's how we're going to measure spin and do all this amazing science. So I mentioned the data downlink. There's a lot of challenges involved with this project, but one of the most fun ones is our data problem. So an interferometer produces a lot of data. It's actually, the Event Horizon Telescope was actually the largest physics experiment by amount of data per night of observation in the history of physics. So to give you some perspective, your average phone or laptop might have a couple hundred gigabytes of data. A terabyte is 1,000 gigabytes, so you can imagine taking 1,000 phones, and that's a terabyte. And then a petabyte is 1,000 terabytes, it's like 1,000,000 phones. The ESG produces about a petabyte of data every night. And you can't store that on the spacecraft. It's actually so much data that we can't even work with it on the ground. Like, you can't upload the data from our sites to like a central server or something, because it would take 30 plus years over a Wi-Fi connection. We have to physically bring these hard drives and put them on planes and fly them to our supercomputers. And that was part of why the first image took so long. There's only 2 flights a year that fly out of Antarctica bringing our cellular data with it. And so we had to wait for that data to get to us. But the founder of the collaboration, Shepard Dolman, he likes to say that when he's running down the hall with all the data, he's the fastest mode of information transfer ever conceived. And he's not wrong, right? He's bringing 4.5 petabytes of data, 60 feet in 2 to 5 minutes. I don't know how long the hall is. But, so how do we solve this problem with our spacecraft, right? We can't actually keep this much data on there. We'll get corrupted by cosmic rays, and also we want our spacecraft to be as light as possible. So having hundreds of pounds of hard drives is just like the worst way to go. Also, you don't want too much storage. Like I said, it can corrupt easily, and we want this thing to be up there for a long time. So we came up with the obvious solution, which was to beam it back down to Earth by a laser. And so Lincoln Laboratory and the VEX project, worked together to produce a 100 gigabit per second laser optical downlink that can beam our data continuously throughout the night of observation back to stations on the Earth that will collect the data, and then we can carry them with our caveman hands to the supercomputer. So that's the premise of VEX for this data. That's how we solve this data problem. Is we'll have small onboard storage, and then we'll be continuously beaming it back down to Earth with a face-melting laser. And we'll, actually, I've been advised to not make that joke. It will not be face-melting. But it will be a very strong laser that can communicate all the data back down to Earth. So, in the last couple minutes, I want to talk to you about just one slide on what I do specifically, which I help out with a lot of the project. I've been involved with it pretty much since its conception. But my primary focus is on measuring spin from the black hole images using this photon ring. And that's actually what this Japan conference was very highly focused on, not just updates on the spacecraft, but also updates on methods that we're actively developing to do this thing that no one's ever done before, which is measure this incredibly fine variation in this black hole shadow shape to capture how fast the black hole is spinning, which I just think is the coolest thing. So the idea is basically this. As you change the spin of the black hole, it looks a little different. And a natural question is can we learn how to use those differences to measure the black hole's spin? And so what I do is I develop, as well as working on the theory of this, so it's really important to have a strong theoretical foundation for why the image looks like this when we change the spin and inclination of the black hole. We also want to be able to extract this information from the image. And so what I work on are these algorithms that can measure the black hole's photon ring from our images and extract, you find patterns to extract and measure these important black hole properties. And so we've got a lot of useful tools and published papers on this exact topic. And it's going to be, I think, one of the most exciting aspects of the project is being able to look up in the night sky with our telescope, flinging itself around the Earth, and be able to measure the spin of the black holes that we point at. And it's something I'm just incredibly excited by. So I want to close off with, with the big picture. I've only had time here to give you a brief overview of some of the mission parameters and science drivers, but I want to do something that I love to do, which is just kind of take a moment to reflect on what we're trying to do here and how crazy and exciting it is. So we're going to put spacecraft in orbit, tens of thousands of kilometers above the surface of the Earth, and connect it via laser to a network of already some of the most powerful telescopes on Earth to create a virtual telescope 3 times larger than the Earth itself. And it's going to see this photon ring of a black hole for the very first time. And this is exciting because the event horizon of a black hole, it isn't just an edge of the observable universe, but it's also a horizon beyond which is new physics, answers to our biggest fundamental questions about the universe. So yes, it's a horizon in the sense that, there's stuff inside that can't get back out. And if you're outside, you do not want to go back in. But it's also a boundary between, the inside of our observable universe and the outside of it, because whatever's in there, we'll never, ever get to see or interact with. And lastly, it's the edge of what we know and what we don't. And that's what I want you to think about when you see these images for the first time. That's what we're probing. So thank you so much for helping us listen to me talk about this and helping us solve the greatest mystery in physics at the edge of the universe. And thank you to SBAU for having me here.